So thank you very much, everyone, for listening to me for the next 45 minutes, I understand. I'm going to tell you about a very general topic, which is layering in fluid dynamics. So that's the formation of layers or staircases in various quantities in something that is fluid. So you might not necessarily associate it with something that could be layered in the first place. But I'll first tell you that layers are actually everywhere in the ocean and in fluid bodies on Earth. So for example, this is a profile of temperature and salinity taken under the surface of the ocean in the tropics. And this is depth, and this is both temperature and salinity. And something that is immediately apparent is this profile is not smooth. And instead of being smooth, it shows a distinct staircase. Now, this staircase is not due to a low resolution of the instrument that took the data. It really is. If you go under the water, you will see a step profile. So to understand it properly, you can see that over layers that are something like 20 to 100 meter deep, the temperature is very constant, and similarly, the salinity is very constant. And then over very thin layers, which can be as thick as between 1 and 10 meters, suddenly it jumps very abruptly. So hence the staircase profile. And you can see that these jumps occur in temperature and salinity at exactly the same time. These layers are very long-lived. They can live for months or years, and they're very wide. They can exist for hundreds of kilometers. So that's in the tropical ocean. And one thing to know about the tropical ocean, if you've ever been there, it's hot and salty at the surface and cold and fresh at the bottom. And I'll get back to that. This is a picture that looks very similar. That's taken as a profile taken in the Arctic Ocean. Now, again, this is depth below the surface. This is potential temperature. Think temperature if you don't know what potential temperature is. And this is salinity. The Arctic is quite special in the sense that there's an intrusion of ever so slightly warmer, ever so slightly saltier temperature water coming from the Atlantic, intruding at depth in the Arctic basin. And that intrusion creates a slightly hotter, saltier body mass of water below a very cold, very fresh surface water. And instead of being smooth, you can again see if you zoom in that you have a very clear staircase profile in the temperature and salinity. And again, the staircases are occurring at exactly the same place in temperature and salinity, with very well mixed layers and very, very thin interfaces. The main difference between the tropical staircase I showed you earlier is literally the overall gradient that is positive in one case and negative in the other. The staircases here are sort of shallower in the sense that each step here is closer to being a meter thick, with the interfaces being on the order of a centimeter. So the overall scale is a little bit different. But so you can see that these staircases exist both in the tropic and in the Arctic. And they're also found in a few volcanic lakes on Earth. So this is an example of Lake Kivu. Lake Kivu is at the border between the Democratic Republic of Congo and Uganda. It's a volcanic lake, so it extrudes CO2, dissolved CO2 and salt from the bottom, and it's very hot, relatively hot at the bottom. And if you go down with the profiler, again you see that over some region of the water, so this is again depth below the surface, temperature and salinity, you can see the same staircases. This time again the steps are about a meter thick, the interface is about a centimeter thick. So it seems to be very common. And so the question is, well, why do they exist? And two, why should you care? It's very cute, but why should we care? Well, I think nobody here is going to argue that understanding climate is one of the most pressing questions of our time. And understanding the climate requires a deep understanding of the interaction, nonlinear interaction between various processes that force the climate and that react from that. And these are microphysical and macrophysical. And among the macrophysical processes, I'm talking about turbulence in the ocean and the atmosphere. And in particular, mixing of temperature and salinity, both vertically and horizontally in the ocean. So the key is that staircases, compared to similar regions with a smoother profile, have vastly different transport properties. So it's been known, for example, in the tropics, this is this work by Ray Schmidt, that if you take this particular profile and measure the overall rate at which it transports temperature and salt across this vertical region. And you take a similar region with a similar overall temperature gradient and salinity gradient, but without a staircase, the transport rate in the smooth profile is much smaller by orders of magnitude. And in the Arctic, this staircase here is thought to control the transport of heat from this warm water to the cold icy water on the surface. And guess why we care about warm water layers sitting in the bottom of the Arctic? You can see there's enough heat in there to melt quite a lot of it. So the staircase regulates the transport of heat from this warm water mass to the upper layers. So it's quite important to understand transport through the staircase. And to do that, we need to understand why the staircase is formed in the first place. So the question is, why do they form? And, well, what is their dynamics? But today I'll just stick to the why do they form. Now, one of the clues to their formation, this is the axis of research that people who've been looking at this problem for ages have been following, is the fact that associated with these staircases, there's a set of instabilities called double diffusive instabilities that always seem to be present. So I'll talk a little bit about double diffusive convection and double diffusive instabilities first, and then go back to the layer formation problem in a minute. So there are two kinds of double diffusive instabilities. They are the kind that occur when you have a hot and salty water lying above a cold and fresh water. So here, the color is temperature, and the density of crystals is the salt. The fingering instability occurs in this regime, and if you take a blob of fluid from the top hot salty water and you bring it down, the first thing that happens is it will want to go back up because it's stably stratified in terms of the density. But if that blob of fluid is small enough, the temperature will rapidly diffuse out, leaving it to be the same temperature but saltier than the environment. And with that, it will now be denser and continue to sink. So the two key parts of the sentences I just gave was that it has to be small, so that temperature can diffuse rapidly, and temperature needs to diffuse more rapidly than salt, because if the salt was diffusing at the same rate, then this process couldn't happen. So that's why it's called double diffusive, and the typical structures that you create are pretty narrow, and in the ocean, they're of order of centimeters. So this is picture, gratuitously cute picture of the tropical ocean, but more to the point, this is an experimental setup that I grabbed from somebody's website that shows warm, salty water overlaying cold, fresh water. And you can see the formation of these little fingers of salty water going down, and there are other fingers that you cannot see of fresh water going up. And that transport heat at some rate that we'll be interested in. Now, there's another flavor of double diffusive convection that occurs when you have cold and fresh water on top of hot, salty water. So now think about the Arctic context. In that case, let's ignore first the temperature stratification and just think about the salt stratification. That salt stratification is very stable. So if you disturb it, it will just excite internal gravity waves that will look like this dashed line. So just wobble up and down. But now if you add a little bit of temperature stratification, when this blob of fluid gets here, it gets a little bit hotter if it's small enough. And that just a little bit of added heat now makes it more buoyant compared to what the wave would have done, and launches this parcel of fluid a little bit further up. When it gets further up, it cools down. So compared to that one, it would be denser, so it will go a little bit further down. So that oscillatory instability is called an overstability, which is a misnomer in my opinion. But it just means that the amplitude of the wave gets amplified by the temperature stratification. Now this happens, like I said, in the Arctic Ocean, or rather this kind of stratification happens in the Arctic Ocean and in the lakes. So all of these places where I mentioned layers exist are also places that have these doubly stratified systems of both temperature and salinity. And that's not, so that the key point is it's probably not a coincidence that everywhere we find the layers are these regions that have this double stratification that could be prone to fingering and oscillatory instabilities. Okay? All right, so how do we put everything together and create a mathematical model for this double diffusive system leading to layering instabilities? So you start with the standard Navier-Stokes equations with temperature and salinity participating in the buoyancy. So this is the momentum equation. So this is the acceleration of a parcel of fluid, and then the forces applied to it, the pressure gradient, the buoyancy force, and the viscosity. The buoyancy force is due to density anomalies compared to the background, and that can be contributed to by temperature. So if it's hotter, the fluid becomes less dense, hence the negative sign. And if it's saltier, the fluid gets denser, hence the positive sign. And the alpha and beta are just these coefficients relating temperature and salinity anomalies compared with the density. And then you just have two advection diffusion equations for the salt and temperature. Now, these equations, I want to be able to resolve them on the small diffusive scales associated with these tiny blobs that I was telling you about. I also want to be able to not have boundaries, because these layers in the ocean, they're usually bounded by two other systems that are not solid boundaries. So I want to have something that's quite flexible. And so the way it's commonly done in these studies is to consider a small region of the ocean, not the entire ocean, and to assume that you have a background temperature and salinity stratification where the gradients are just constant. So I have a linear profile of temperature, which is just the mean temperature plus z times the gradient of temperature. And then the salinity is the median temperature, median salinity plus z times the salinity gradient. And then on top of that, you have perturbations. And then we want to make advantage of spectral codes in fluid dynamics, which are extremely fast. And so we're going to assume that the perturbations themselves are triply periodic in the computational domain. Okay? So then you can do Fourier, 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 and it's really blindingly fast. Now, with the assumption that the temperature can be broken down into a background plus a perturbation, you plug that into these equations. And then you non-dimensionalize them based on length scales associated with the expected width of the fingers, or the blobs in the oscillatory case, the temperature, the time scale of diffusion, the typical jump in temperature across that scale, and jump in salinity across that scale. And you end up with these equations, which are the non-dimensional versions of the one I showed you earlier. And then you have these extra terms here, the plus and minus W and plus and minus W over R naught. Now, and these come from the contribution of the background temperature and compositional gradients. And out of that pops three non-dimensional parameters: the Prandtl number, the diffusivity ratio, and the density ratio. So the Prandtl number is the ratio of viscosity to thermal diffusivity. The diffusivity ratio is the ratio of salinity diffusivity to temperature diffusivity. And the density ratio is the ratio of the density gradient due to temperature to the density gradient due to salinity. Now, this is a really crucial parameter, so I'm going to tell you a little bit more about it. So for instance, when this density ratio is 1, you can rearrange the equation and write it minus alpha times temperature gradient plus beta times salinity gradient equals 0. And that's exactly the density gradient. So when this density ratio is 1, you're exactly neutrally stable in terms of the density. You know that if density goes up, as you go up, then you're top heavy and you're going to convect. Whereas if the density goes down as you go up, then it's stable. And that density ratio equals 1 is exactly neutrally stable. And then in the fingering case, this density ratio, if you look at it, it's basically temperature gradient over salinity gradient. The temperature gradient is the stabilizing component, and the salinity gradient is destabilizing. So the larger this number is, the more stable it is. Okay? And in the oscillatory case, you switch the stratification, and so this density ratio becomes the ratio of the destabilizing component to the stabilizing component. So the larger it is, the more unstable the system is. So it just switches. And going back to these equations, the plus and minus signs here just refer to the fingering case for plus and the oscillatory case for minus. So we have these two completely different instabilities, and the only thing that distinguishes them is the sign of these two terms from a mathematical standpoint. So from a coding perspective, it's wonderful, right? Just go in my code, change a sign, I can explore a whole new range of parameter space. So this is just to summarize a little bit the parameter space. So if you don't have any salinity gradient at all, this is what people know quite well, is that if your density gradient is positive, so it's top heavy, you're convecting. And if your density gradient is negative, you're bottom heavy, you're stable. So this is the standard picture of convection. Linear stability analysis shows that if you add a salinity gradient that's top-heavy, so more saltier at the top, then you extend the region of parameter space that's overturning unstable, and then you tag on a huge region of parameter space that's fingering unstable. So suddenly, you're unstable pretty much any time. In the case when you add a salinity gradient that is negative, so you have more salt at the bottom, it becomes harder to be convective because you've stabilized the system. So the region of parameter space that's unstable shrinks. And then you add on a little bit of region that is unstable to oscillatory convection. Okay? So that's just to summarize what happens, and I'll come back to this picture a little bit. This is linear stability. This is what these instabilities look like from a numerical perspective. So these are numerical simulations using our triply periodic code. This shows the salinity, for example, the salinity perturbations over the background, sorry. And you see very quickly that you have these blobs of salty fluid going down and blobs of fresh fluid going up, as we expected. The next one is the oscillatory instability. So that one's a bit trickier. Initially, you started with these columns, but rapidly it becomes wave-like. And I'm sorry, the cadence of the movie is pretty bad, so it just looks jagged, but in reality, it's just sloshing around, okay? So you have these waves of salty material sloshing around and waves of fresh water material sloshing around. So this is what these things might look like once they become nonlinear. Okay. So the key to take from these nonlinear simulations is that the turbulence is small scale, as I described earlier, because you need the temperature diffusion to be fast. And that, in general, is pretty homogeneous, right? It might be anisotropic, but it's quite homogeneous. But now, if you take one of these simulations, namely the oscillatory one, and you just run it for a lot longer, this is what happens. And I've changed the color scheme to confuse you, but I'm just showing exactly the same thing. This is the same simulation as before. This is, again, the salt perturbation. And you see the sloshing around. This time, the cadence of the movie is a lot nicer. But you can see it doesn't stay homogeneous. This is one of these examples where suddenly you can see now the formation of 3 layers. This one is getting fainter, and it merges with the second one. And then suddenly things get more violent. The convection gets stronger. The interfaces wobble a lot more, and suddenly the third one disappears, and you're just left with a single layer. Okay? And this just happened without any forcing from our perspective. It just happened on its own, just by waiting long enough. So it really appears that if you take a very basic double diffusive system and then you let it sit there for a while, it will become layered naturally. The ocean tells us that, and the numerical simulation suggests that is the case. So why do these layers form? So don't let me fool you. There's a lot of theories out there. I'm going to present to you my favorite, because I think it works. Okay? This theory was not put forward by me. It was put forward by a colleague of mine called Timur Radko at the Naval Postgraduate School. And the theory is somewhat mathematical, so I'll walk you through it. I'll walk you through the basic at the beginning, and then I can, those of you who can't follow the math, you can fall asleep for a bit, and then you can come back. But just the basic idea is quite simple. So I showed you earlier that we have perturbations on top of a background gradient that is constant. And I'm going to consider a horizontal average of the temperature and salinity fields. So it's just horizontally average is the overbar. So the onset of layering implies that on top of that background that has a constant gradient, I'm starting to have wiggles in the temperature profile and salinity profile. And these correspond to non-zero value of these horizontal gradients. Okay? So when layering starts, these become non-zero. And this happens because they satisfy a conservation law. This is a very standard conservation law saying that the derivative of the temperature, the mean temperature, is minus the flux of the derivative with respect to z of the flux of temperature. And the derivative of the salinity with respect to time is minus the derivative of the flux of salinity with respect to z. So the divergence and convergence of fluxes changes the mean temperature and salinity. And that's an exact equation. You can derive it from the full Navier-Stokes. Now, these fluxes are typically, they're contributed to from turbulent fluxes, so the correlation of the vertical velocity and temperature and vertical velocity and salinity. But that's almost irrelevant. The whole theory works even if this isn't true, so you just start with that. So there's key assumptions in the theory, and it's a bit difficult sometimes to distinguish them from what's a definition. So I'm going to try and tease out what's a definition and what's an assumption. So the first thing is, so these are these fluxes that you measure from the numerical simulation. I'm going to relate them to the background temperature gradient. I'm going to relate it to the local temperature gradient, which is the sum of the background, which is plus or minus 1 plus the derivative of temperature with respect to z, and the plus or minus 1 plus for fingering minus for oscillatory. So, and the thing that relates them is going to be this Nusselt number, and that's just a number. And it's a function of temperature, salinity, temperature gradient, salinity gradient. It can be a very complex function, but the key is it's local. So I'm not allowing time delays, and I'm not allowing far field interactions. Okay? So there's a local function relating the turbulent fluxes to the temperature gradient. And then I'm also going to define this ratio of the fluxes, temperature flux to salt flux, and I'm going to assume that ratio is a local function of the local conditions. So no delay, no long-term interactions. Gamma is just a function of temperature, salinity, temperature gradient, salinity gradient. And note that these numbers are non-dimensional, and they've been constructed to be non-dimensional. So that's what I mean. Most of this is just definitions. The two assumptions in here is that these numbers that I've just constructed are local. So with these definitions, now I'm making assumption, well, maybe not, is that these non-dimensional numbers, the Nusselt and the flux ratio, are only functions, because they're themselves non-dimensional, they can only be functions of non-dimensional quantities. A non-dimensional number cannot be a function of a dimensional one. It has to be a function of a non-dimensional one. And the only non-dimensional numbers in the system, if you look back at the governing equations, are, look at these non-dimensional numbers, the Prandtl number, tau, and the density ratio. So this Nusselt number and this flux ratio, they have to be functions only of these three quantities. So Prandtl number and tau are just dependent on the fluid properties. But on the other hand, the density ratio, now I'm going to have to assume it's a local density ratio that cares about the local temperature gradient and local salinity gradient. So this was the original density ratio from the background temperature and salinity profile, and then I take the actual temperature gradient. So the sum of the background plus the local temperature gradient, and here's the sum of the local salinity plus background salinity plus local salinity gradients. And non-dimensionally speaking, it looks like this. And again, plus or minus refers to plus for fingering, minus for oscillatory. So these are the governing equations for layer formation. You can see it's a two conservation laws and some assumptions for closing the fluxes as a function of the background quantities. And the first thing to note is that this set of equations admits a set of trivial solutions. So if you're just allowing solutions that don't have large-scale perturbations in temperature and salinity, this is 0, this is 0, this is 0. So the density ratio is the background density ratio. The flux is minus the Nusselt number associated with the background density ratio. And the salinity flux is given by Nusselt and over gamma. The point is, this solution is the homogeneous state of fingering convection, so what I showed here, and the homogeneous state of oscillatory convection, which should have appeared here. So you can measure these things from the numerical simulation. I run the simulation long enough, I get into this homogeneous state, and I can measure the heat flux, and I can measure the ratio of the heat flux to the salt flux. This is just a question of measuring them from the data. And now, to get into layers, this is the results, for example. This is an example of what the Nusselt number looks like and the flux ratio looks like as a function of the density ratio for fingering convection at Prandtl 7 and diffusivity ratio 0.3. The numbers are almost irrelevant. What I want to show is one of them is monotonic. So the Nusselt number is monotonic function of the density ratio, whereas gamma is non-monotonic. It has a decreasing part and an increasing part. And note that for fingering convection, this is very unstable, and as density ratio increases, it becomes very stable, hence the decay in the turbulent transport rate. Now let's move on to how you actually form layers. So I'm going to start with a big picture perspective. So I said that when you want to form layers, you have to start creating large-scale perturbations in temperature and salinity. So these are here. So now I have non-zero large-scale temperature gradients, large-scale salinity gradients. These are going to perturb the local density ratio. So this number now is no longer just R0. It's going to be something that varies with Z. Because this density ratio varies with height, the Nusselt number and gamma are going to vary with height, and therefore the fluxes of salinity and temperature are going to vary with height. They're no longer constant. And you know what happens in a conservation law when you have fluxes that vary with height? You're going to start accumulating the quantity in a region and decreasing in other regions through these equations, these conservation equations. And in some cases, you're going to have a positive feedback loop in which the change in the fluxids leads to a reinforcement of the original perturbation. And in other cases, you'll have a negative feedback loop where the change in the fluxes will kill the original perturbation. But the positive feedback loop is what's going to drive the layering instability. So that's kind of in a hand-wavy way. In a slightly more detailed way, you go back to the full equations. And then what you do is you assume that initially these perturbations are small. So they're small compared to the background. So that gives you this relationship. And you're going to linearize these PDEs around that background, which has constant density ratio and constant fluxes. So this, for the first year undergrads who learn calculus, this is the power of the product rule and the chain rule. So, and Taylor expansions here. So for example, you can take the density ratio. And now, if you know this is small and this is small, you can do a Taylor expansion and write it as a background density ratio plus a perturbation. And you know what this R prime is as a function of the perturbation in the temperature and salinity field. So that's just the Taylor expansion. This, in turn, is going to affect the Nusselt number. So Nusselt number of background R0 plus R prime. If R prime is small, you Taylor expand and you get this expression. So that's telling you that if you have changes in the density ratio, that's going to affect the Nusselt number for small enough perturbations, and similarly for gamma. And then you plug all of these into the governing equation for the temperature, for example. So the flux of temperature is Nusselt times 1 plus Tz. You take the product rule, so that's d nu dz times this, plus nu times tzz, so that's the second derivative of t bar. So that's exact. And now you linearize, and you get rid of any terms that are second order in perturbations. And then you also note that d nu dz, the only reason the Nusselt number changes with height is because it's a function of r prime. And so you say that's d nu dr, dr dz. And off it goes. And then you get an expression that just depends on constant times second derivatives of temperature and second derivatives of salinity. Okay? So the upshot is the change in the background temperature is related to this. So second order partial derivative with respect to z of temperature and salinity. And you have a similar equation for the salinity. Now these are PDEs which are linear with constant coefficients. So the standard ansatz is to assume that everything varies like e to the ikz plus lambda t. So the d2 by dz2 becomes k squared. The d by dt becomes lambda. You fold everything together and you end up with a quadratic equation for the growth rate of these layering modes. Then the nice thing about this model is the math is extremely simple in essence, because you end up with a quadratic. Everybody pre-calc level knows how to solve a quadratic. The first term is positive, so it's an open-up parabola. So under which conditions do you have solutions with positive values of lambda? Well, you just make sure that the last coefficient is negative. So if the last coefficient has to be negative, it gives you a necessary condition for instability. And since the Nusselt number is positive, Nusselt square is positive, density ratio is positive, K4 is positive, the only requirement is that this A gamma, which happens to be related to the derivative of the gamma function with respect to the density ratio, that has to be positive. Okay? So you have a layer instability if d gamma dr is positive, d inverse gamma by dr is positive, hence the name, the gamma instability. If that happens, the perturbations grow, and eventually the density becomes top-heavy and overturns into a staircase. And that's the picture. So to sum up, you have a theory in which you make a few assumptions and you predict that layers should form if the flux ratio, so the ratio of the temperature flux to salinity flux, is a decreasing function of the density ratio. Physically, it corresponds to an anti-diffusive behavior. So anti-diffusion is when you have a diffusion equation but with a negative diffusion coefficient. And that has a few nasty properties that implies that you have an ultraviolet catastrophe where the smaller scale modes grow the fastest. So that's a problem with this theory, but let's ignore it for the moment. I mean, it's okay, because in practice, when you get below a finger size, it doesn't make sense to think of a layer that's as big as a finger, right, for example. So it's okay. It's a mathematical problem, but in reality, it never happens. So the big question is, does this work? So you can test that. Remember I showed you earlier that this gamma curve decreases with density ratio at these parameters? So you can just pick a point here, pick a density ratio, and run a big simulation. Let's do that. So I'm going to show you, again, the salinity perturbations in a big box for these parameters. It's going to go pretty quickly at the beginning. You have the development of the fingering instability, and then we expect layers, right, from this theory. It's not what you get. You get waves, right? So instead of getting the layers we expected, we end up getting what turns out to be internal gravity waves. This, as it happens, comes from a completely different instability of fingering convection called the collective instability. And that has also been known a long time. But as it happens, it coexists with the layering instability. And it's the one that grows the fastest. So that's why you see it now. And we have a completely different theory of how that that collective instability grows. I'm going to skip forward in the interest of time, just to show you that even though you don't see it, layers have been growing all along. And if you just wait a little bit longer, you start seeing that the phase planes of the waves start tilting towards the horizontal. Now you start seeing that, if you blink, you'll miss it. So you see now that there's these lines here and here. And a few bits now, it becomes convective. Instead of being small fingers, you see overturn here and here, right? And now the layers, you really have this accumulation of dense material. And then it sharpens instantly almost. And then everything in between these interfaces becomes fully convective. And if you look at the profile of the temperature in that, it's exactly as I showed you. It's completely constant in the convective regions and very sharp at the interface. You can predict, I'm going to skip that, you can predict the layer growth rate from the theory, and you get a number. And then you can compare it with what the layer growth rate in the actual simulation was. So this is a plot showing time on the x-axis. And then on the y-axis, it shows the energy in two different modes. It shows the energy in that gravity wave mode that we were talking about, that grew very rapidly and dominated the simulation for a really, 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 really long time. And then on top of that, there's a potential energy in the layering mode, and that's the blue curve. And you can see it's been growing all along. It was just hidden in the wave noise. And the pale blue curve is the predicted growth rate from the model with no fitting, okay? So you can see that the layer growth rate predicted by the model works really well to explain the actual growth rates in the simulation. And that's a validation of this theory. So it predicts not only when the layers should form, but also at what rate they should form. So let's go back quickly now to the oceanic staircases I was telling you about and see what the model would predict then. So both for the tropical staircases and the Arctic staircases. So let's start with the tropical staircases. You can do fingering simulations at now actual water, Prandtl number, and diffusivity ratio. It's pretty challenging. This is what they look like. Sorry, you can't see it very well. And you measure this gamma flux ratio as a function of the density ratio. And you predict that layers should form whenever this is decreasing, so all the way to density ratio of 4. Now, if you remember, I didn't quite show it very well, but the growth rate of the layers is actually proportional to the gradient of gamma with respect to r. So the sharper the decrease, the faster the layers grow. So you expect that the layers would grow rapidly here, but slowly here. Okay? And so the growth rate should be quite large for density ratio smaller than 2, but could exist all the way to 4 with much smaller growth rates. And this is what you see in the ocean. You see that in the tropics, the staircases are only found in regions where the density ratio is between basically 1 and 2-ish, which is where this predicts that the layers would grow the fastest. So the regions where they actually appear in the ocean seems to correspond to what we predict from the theory. And then you can compute the growth rates and predict they should grow on the order of days to weeks. And this is, again, what we predict from the theory. This is, again, what's seen in the ocean, so they're consistent. So the conclusion is the tropical staircases are probably formed by this gamma instability theory. Now let's talk about the Arctic. And that's you have a beautiful theory, you have beautiful staircases, and you think the beautiful theory should explain the beautiful staircases. But if you actually you try to compute the fluxes, you do numerical simulation if you want to for the Arctic Ocean, you fall flat because the Arctic Ocean is not actually unstable to the oscillatory instability. The range of instability for the oscillatory instability is when the density ratio is between 1 and 0.84, using Prandtl number 7 and tau is 0.01, which is appropriate for salt water. Whereas these staircases have much smaller density ratios, so they're actually stable. So the point is, they could not have formed through this cascade from basic instability to layering instability. So tropical staircases are formed by the gamma instability, and Arctic staircases, we still have no idea. There's a few theories floating out there that are very promising, but I think nothing is quite set in stone yet. So basically, although it looks like a duck and quacks like a duck, it's probably not a duck. And it's a nasty thing. Okay, I'm going to take a couple more minutes to talk about what my favorite topic is, which is layer formations in astrophysical objects. Now, there's no data, or almost no data, so I can say whatever I want, right? It's not quite true that there's actually some data, but it's always data by proxy, because you never see the layers. You see something like chemical abundances of a star that's not quite what you should have without layers. I mean, it's very, very much by proxy. But anyway, there's no reason not to do exactly what we've done, to run numerical simulation, to compute the gamma of our function and predict whether layers should form or not. It's important to know whether we might actually have double diffusive instabilities in the first place in astrophysics. And that we do know is that fingering instabilities, which happen when you have heavier elements at the surface than in the interior, that can happen, for instance, when a planet plunges into a star. Okay? Oscillatory instabilities that occur when you have dense elements at the bottom of the star, that often happens in core convective stars or in giant planets, which are formed by core accretion. In both cases, sorry, I kind of skipped that. It's so obvious to me, but maybe not to you. There's no salt in astrophysical objects, or very little. Helium basically plays the role of salt, right? Or carbon, nitrogen, oxygen, so heavier elements. So these instabilities exist, but are they layered? It's also important to know that the Prandtl number and the diffusivity ratio are quite different. So these are geophysical parameters, so fairly high Prandtl number, very high diffusivity ratio. These are astrophysical parameters. Stars are really the outliers. They have extremely low Prandtl number, extremely low diffusivity ratio. So it's quite challenging numerical simulations to do. This is simulations done by former grad student Adrian Traxler, looking at lots of various sets of simulations with different low Prandtl number and diffusivity ratios, plotting this function gamma of r. And as you can see, it always increases for any set of simulation. And we actually, now, it's been a few years, we actually understand very well why it increases, right? So it's not just these simulations, it's really robust. So the prediction is, if layers exist in fingering regions of stars, they could not have formed by the gamma instability, full stop. Okay? Whether it doesn't say they can't be layers, it's just they could not have formed by this mechanism. Now, somebody in this room did the same thing for the oscillatory case, looking at the function gamma of R, or more specifically, the inverse gamma as a function of inverse R, and computing them again for lots of different Prandtl numbers and diffusivity ratios. And in this case, there's a significant region of parameter space where they do decrease. More significantly, wherever there's a big symbol, these are simulations that ended up in the staircase. Okay? So not only there's a decreasing part of this curve, but everywhere it's decreasing, you get a staircase. So that's a good validation of the theory. And the prediction from that is that layers formed by Radko's mechanism in stellar interiors, and they are ubiquitous. They are almost always there. So that's quite interesting. And it has implication for stellar evolution. As you saw in the movie earlier, they're there, but they don't stay there. They merge and merge and merge and merge. And that also has implications for stellar evolution. I'm going to leave it at that. So generally speaking, so I've been studying one kind of layering instability in this talk. It seems to work for two things. This is all the topics I've discussed. I've talked about fingering instabilities in the tropics. And in that case, these staircases are probably formed by Radko's instability. I've talked about Arctic staircases. And in that case, they cannot have formed by that instability. Something else happened. I've talked about fingering in stars and demonstrated that these layers cannot form by the Radko mechanism. And on the other hand, oscillatory convection in stars, which often happens in core convective stars and giant planets, these are expected to form by Radko's mechanism, and it has a big implication for stellar evolution that we are exploring. So I think that gave you a little bit of a survey of parameter space for one layering mechanism. Okay, thank you.